Welcome to today's Explainer. Look, if you've ever felt completely bogged down by the messy, complicated algebra of parabolas, you are in exactly the right place. Today, we're going to entirely bypass the tedious process of completing the square. Instead, we're unlocking a mathematical cheat code for graphing standard form quadratics. We are literally going to change how you approach these equations forever. Okay, here's our roadmap. We'll start by looking at the vertex shortcut formula. Then we'll build out a graphing playbook, and finally, we'll put it all to the test against 3 distinct boss battles. Case 1 with 2 intercepts, Case 2 with 0 intercepts, and Case 3 with just 1. Let's get right into it.
Part 1. The vertex shortcut formula. To really grasp this shortcut, we kind of have to zoom out and look at the fundamental geometry of a parabola. Think about it. A parabola is a perfect mirror image of itself, right? Which means its axis of symmetry, that perfectly straight vertical line right down the middle, sits exactly halfway between its x-intercepts. So if you know where the curve crosses the x-axis on the left and where it crosses on the right, the absolute dead center of those 2 points is where your axis of symmetry lives. And crucially, sitting exactly on that line is your vertex. Now, watch what happens when we do something a little clever. We already know the standard quadratic formula gives us those x-intercepts, so to find the exact middle of them, we just average them. And here is the magic part. When you add those 2 messy parts together and divide by 2 to find the average, those complicated plus and minus square roots, they completely cancel each other out. Just poof, gone. What we're left with is negative 2b over 4a, which simplifies beautifully.
And that brings us to negative b over 2a. That's it. That's your cheat code right there. The big takeaway is that anytime you're staring down a quadratic in standard form, calculating the exact x-coordinate of its vertex is literally as easy as taking negative b and dividing it by 2 times a. You absolutely do not need to complete the square. And honestly, you don't even need to find the x-intercepts first.
Part 2. The graphing playbook. Now that we're armed with our ultimate shortcut, let's build a reliable, universal framework, a playbook we can use every single time. Step 1. Find where the curve crosses the x-axis, just by setting y to 0. Step 2. Deploy our brand new negative b over 2a cheat code to lock in that middle vertical line. Step 3. Take that x value, plug it right back into the original equation, and that gives you the exact height of your vertex. And finally, step 4. Grab your y-intercept, which is always just that c value at the end of the equation, and use it to sketch out the rest of the curve. Simple, repeatable, and bulletproof.
Part 3. Case 1. 2 intercepts. Okay, time to put this playbook to work. Let's test it out on a pretty standard equation. Y equals negative 5x squared plus 8x minus 3. As you'll remember, step 1 of our playbook is setting y to 0 so we can hunt down those x-intercepts.
If we go ahead and factor this, we find our intercepts are sitting at 0.6 and 1. But watch the cheat code at work here. If we take our b value, which is negative 8, and divide it by 2 times our a value, which is negative 5, we instantly get 0.8. Notice how 0.8 is the absolute dead center between 0.6 and 1. Flawless.
Moving on to step 3, we just take that 0.8 and plug it back into the equation for x. When we do that, we find our highest peak, our vertex, has a y-coordinate of 0.2. And for step 4, we just plot our y-intercept way down the y-axis at negative 3. Because parabolas are perfectly symmetrical, we can just mentally mirror that y-intercept across our axis of symmetry, plot one more point, and boom, a beautiful, perfectly accurate parabola.
Case 1 went incredibly smoothly. But we have to ask, what happens when the math tries to break our rules? What happens if you get a negative discriminant? That part hiding under the square root in the quadratic formula? If that is negative, things get a little weird.
Part 4. Case 2, 0 intercepts.
Enter our second boss battle, the floating parabola. Let's look at y equals 2x squared minus 8x plus 11. If we try to blindly follow step 1 and use the quadratic formula here, we hit a massive brick wall. We end up trying to take the square root of negative 4. And since no real number multiplied by itself equals a negative, traditional rules just kind of break down.
But right here is where the true magic of our cheat code shines. Even when the parabola completely floats and never once touches the x-axis, meaning there are literally 0 real intercepts to average, our negative b over 2a formula simply does not care. It still flawlessly locates that axis of symmetry. Watch. Negative 8 becomes positive 8. Divide that by 4, and we land squarely at x equals 2. The cheat code survives.
Sticking to the playbook, we plug that x value of 2 back into our equation, and it spits out a y value of 3. So our vertex lives exactly at the point 2, 3. Now, our y-intercept for this one is way up at 11, which might completely fall off your graph paper. No big deal. We just grab a couple of symmetric points around the vertex, let's say at x equals 1 and x equals 3. We find they both have a y value of 5, which gives us everything we need to finish sketching this completely airborne parabola.
Part 5. Case 3. 1 intercept.
We've conquered 2 intercepts, we've conquered 0. Let's face our final boss, the perfect square. Take a look at this equation. Y equals x squared minus 10x plus 25. When we try to find the x-intercepts here, we realize it actually factors incredibly neatly into identical binomials, x minus 5 times x minus 5. Because setting that to 0 yields just one single intercept right at 5, it means the vertex itself has to be the exact spot where the parabola sort of just kisses the axis. Let's verify it. Deploying our cheat code, we take -10, divide by 2, and what do you know, it matches perfectly, putting our axis of symmetry exactly at 5. To wrap up the playbook, we plug our 5 back into the original equation and confirm the y-coordinate is, in fact, 0. That means the vertex sits flawlessly flush right on the x-axis at 5, 0. From there, plotting a couple of symmetrical points on either side, like at x equals 4 and x equals 6, gives us the rest of our curve.
Look at this summary. It brilliantly shows just how gracefully this single simple cheat code handled absolutely everything we threw at it. A standard parabola? Handled. A totally airborne floating parabola with 0 intercepts? Handled. A perfect square sitting right on the axis? Handled. No matter what standard form quadratic you're facing, the fundamental symmetry of the shape is always there and the cheat code always holds true.
So you now possess the ultimate framework to completely deconstruct and graph literally any standard form quadratic that comes your way. You know exactly where the formula comes from, why the math works, and how to rapidly deploy it. You're going to save so much time and drastically cut down on algebraic errors. So the only real question left is, what equation are you going to conquer next?